Hey, Dr. White here with some solutions for the Chapter 3 homework. Let's start off with number 2 in section 3.1. So you're given the PDF for some random variable capital X, and its support is only from 0 to 1. You got to find this undetermined constant C for the part A of the problem. And so you say, well, the area under a PDF ought to be 1. Total area should be 1. So you say 1 equals, and then I would not actually immediately write down this integral without really carefully thinking why, because 1 really is all you're sure of is that 1 is the area from minus infinity to infinity under f of x. But then that can break up as the integral from minus infinity to 0, integral from 0 to 1, integral from 0 to infinity. And the support is 0. The support's only between 0 and 1. And so f of x is 0 in this range and 0 in this range. So the only non-zero part of the integral will be the 0 to 1 range. So if you're not writing that down explicitly, please do at least be thinking about it every time you think about integrating under a PDF, because you really have to consider ideas of support. You can trip yourselves up if you only leap for the formula sometimes. Okay. Well, anyway, between 0 and 1, f of x is equal to that. And fundamental theorem of calculus comes in, plug in the 0 and the 1, you get c over 6. So you get the equation 1 is c over 6, so c is 6. And then after that, it's easy. If you need the probability that capital X is between 0.3 and 0.6, then you just integrate from 0.3 to 0.6. And over that range, the f of x is just the c times x minus x squared. And so it's pretty easy to get something that you could just leave like this, or you could put into a calculator and simplify to about 0.432. Third part of the problem is find the median of x. Now, here's an important thing about homework. The purpose of homework is not to get it done for a good grade. The purpose of homework is for you to have opportunities to develop yourself as a mathematician and specifically as a probabilist. Good textbooks don't give you homework problems where to solve them you have to go through long, meaningless, boring computations. You're going to have to use insight to avoid the long, meaningless, boring computations in quite a few problems, okay? So if you ever find yourself at a point where there's a long, meaningless computation ahead, or it looks like you're going to have to go to a computer algebra system or Wolfram Alpha in order to find the integral or solve the equation, then ask yourself, is there an insight into the structure of the problem that I'm missing right now, okay? So let me explain to you a bit by talking about the tough way to find the median. You can just pull out the definition and you can say, okay, the median is going to be the number pi sub 0.5 such that the chance of capital X being less than pi sub 0.5 is 50%. And so you can set up 50% is the area under the PDF from minus infinity to pi 0.5. And that'll just be the integral from the beginning of support 0 up to this unknown pi 0.5. And here's the formula for f in the range between 0 and 1. And so you got an equation, and you just use the fundamental theorem of calculus, and you get this equation. And that is a cubic equation in the unknown pi sub 0.5. Now, we got the quadratic formula to solve quadratic equations, but the formula for solving cubic equations is super complicated and nobody ever learns it anymore. So here is a big slog of a computation, okay? Now you could go to Wolfram Alpha or something and ask it to solve, this for x, and you'll get 3 solutions. And I think one of them is negative, and another one's bigger than 1. There's only one of them, namely 1/2, that is in between 0 and 1. And we know the median is going to have to be somewhere in between 0 and 1 because it's got to deal with the support. So we could get it that way, but look for an insight around it. The easy way, based on the insight, is to just imagine the graph of 6x minus 6x squared over its support. This is a quadratic function. Its graph is going to be a parabola, and it's going to be opening down because of the negative 6 coefficient. And it hits 0 at 0 and 1. And so a rough graph looks like this. And we know the vertex is halfway in between the two places where you cross the x-axis for parabolas. So the vertex, the high point here is over a half. Just for fun, I found f of 1/2. And then I think about this. I'm looking for a number so that half of the area under the curve is before that number. Well, this graph is symmetric around x equals 1/2. So the area before a half has got to be the same as the area after a half. A half has got to be the median, okay? That's the insightful, easy way to solve the problem. Look for the insight. Develop yourself as a mathematician, as a probabilist. Do not run to computer algebra systems unless you have struggled to look for insight. Do not go to the internet and look up solutions for these homework problems. I know they exist. Look for insight. If you cannot find the insight and you have to go to Wolfram Alpha, do so, tell me that you did, and then make a note. Is there an easier way? And we'll talk about it in class so that we can develop these insights. It's not about the good grade. It's not about getting it done quickly. It is about developing your mind, okay? Number 6 from 3.1. So this is the one about the expected profit for the watermelon dealer, okay? And the number of people who want watermelons is approximately a uniform random variable between 0 and 200. And we worked in class on the profit that she would make as a function of how many people want to buy watermelons, and it was this piecewise defined function. Okay, and I'm calling this profit function P sub n because it depends on how many watermelons she decides to provide that day. That's a choice she gets to make. She doesn't get to determine the capital X. And we needed to find the expected value of P sub n of x, and then after that, figure out what value n would maybe maximize the expected value. So the expected value of any function of a random variable is the integral from minus infinity to infinity of possible values of the function of the random variable times the chance of getting each possible value of capital X. And so that's the f of x dx part. Okay, and then we think to ourselves, well, f of x is the PDF of a uniform 0 to 200 random variable. So its support is only from 0 to 200. So the integrals only go to 0 to 200. And between 0 and 200, 1 over 200 is the value of little f. Okay, so then we think, well, what about P of x? Can we work in a formula for, and that should be a Pn of x, by the way, that's a little typo. I'll fix it here on the sheet, but I don't think it's worth like rescanning in. You can tell this should be a Pn of x, just like this should have been a Pn of x. Okay. The thing is that Pn of x is piecewise defined. Its formula is different over two ranges. If the capital X came out between 0 and n, or I should say if the little x, the little possible value is between 0 and n, then the first formula holds. And if it's from n up to 200, the second formula is appropriate. So you have two integrals to work with. So far we're up to where we were in class. And I think that's where we stopped in our hint. You now want to think, gee, I got a lot of integrals. What kind of insights can I generate here to make my computations easy, not too hard? One thing is to go ahead and try to simplify your integrand before you break the integral up into multiple parts, okay? Same here. So I'm going to make my simplifications, and this simplifies to this. This simplifies to this. So there's fewer terms to deal with there. The 1 over 200 is common, so I'm just going to go ahead and pull that out and of both big terms. Okay, so think ahead about how do I set my work up so that I have the least amount of stuff to look at any one moment. Okay, and then fundamental theorem of calculus seems to be about the best I can do, so I do that. And then I plug in the value in, the value 0, and just get this. And here I plug in the value 200 and get this, and I plug in the value 0 and I get, in fact, I plug in the value in and I get this. Okay, good idea to simplify before you go any further. Okay, so I simplify the best I can. I just gather some like terms and stuff. Here's 3/4 of an n minus half of an n, so that is a 1/4 of an n. And here's 6n squared minus 2.5n squared, so that's 3.5n squared, so I got a minus 7/2 n squared. And I see a little more chance for simplification. The 1/4 minus a 14/4 would be a minus 13/4. Okay, that's as simple as I can make the expected value of p sub n of x. So I'll think of that expected value as some function of little n. And if I think of it that way, then I'm looking at a quadratic function. So its graph is going to open down. So I know that there will be an absolute max at the unique critical point. Okay, so all I got to do is find out where the f prime of n is equal to 0. And so I just take f prime of n. And I set it to 0 and I solve, and I get about 184.6. So, if she's got to provide a whole number of watermelons, it's either going to be probably either a 184 or 185, and you could check if you wanted which one is best. And this is totally fine as a final answer. You're approximating capital X anyway as a uniform when it's really, not. Okay, number 16. Here you had to find 3 percentiles for a little distribution given here with this PDF. The best thing to do first is to find the CDF of the distribution. So that's the probability that capital X is less than or equal to little x for some choice of little x. So that's the integral minus infinity to x of f of t dt. Need to change my variable here because I already got an x up here. And so thinking in terms of support, this comes down to the integral from minus 1 to x of the formula, t plus 1 over 2 dt. Okay, so fundamental theorem of calculus, plug in, simplify. Now that is going to be the correct answer for f of x if x is between minus 1 and 1, because this little move from here to here is only valid if x was between minus 1 and 1. Like if x were bigger than 1, then we would be looking for the chance for capital X to be less than or equal to, that x. That would be 100% chance because capital X can't be bigger than 1 anyway. So this formula here was assuming that x is between minus 1 and 1. The actual full accounting of capital F of x is that it's 0 if x is less than the lower bound of its support, and it's 1 if x is above the upper bound on the support. The formula we got only applies in between. Okay, now say you wanted to find the 64th percentile, which is part A. And so by definition, the 64th percentile is the number that has 64% of the area below it. That is, it's the number where the probability of being less than the 64th percentile is 0.64. So that's just a definition set up. Now, The 64th percentile has to lie somewhere in the support. So I just get to throw that on and solve gradually for pi sub 0.64. But you can also make your work easier by thinking ahead. Again, insight over grunt work. When you read this problem, and you should read the whole thing before you do it, then you actually see that you're being asked to find 3 different percentiles. Why do the same grunt work 3 times? Maybe just do it once. So if you were to just do this same work where there's any p here, any decimal between 0 and 1, and same p here, and have just p's instead of the 0.64, then you would end up with pi sub p is square root of 4p minus 1, which is the same as square root of 2p minus 1. One little detail is, like, when you are taking the square roots, a square root of 4p, how do you know to use actually the positive result? Because when I am going here, something squared is 4 times 0.64. Really, all I know is that the something is plus or minus. Okay. And so when I carry along, the something is plus or minus this square root minus 1. How did I know to switch to the positive? Well, that's because if I used the negative square root here, then the percentile would have been a negative number minus a 1. That percentile would have been less than negative 1. But that's outside the support of the random variable. No percentile could be there. And so I have to choose the positive at this step. And that's why I'm seeing a positive root 4p minus 1 in my formula. Okay, so it really is important to think about supports. That's part of your building up of insight into probability. Anyway, once you get that formula, if you just work the formula out, then you could just slug in 0.64 right here and get part A right away. And similarly, you could get parts B and part C right away instead of having to go and solve 2 more equations. Insight over grunt work. Number 8. They say X is a gamma, alpha is 2, theta is 4, so it's like you're waiting for 2 events in a Poisson process where events occur 4 time units apart on average. Need the chance that X is less than 5. Well, there is a grunt way to do it where you would just a grunt way would be to just go ahead and do the integral from 0 to 5 of the PDF of your gamma. And when you plug in what you know, you end up with an integral that is not so hard to do. It does require integration by parts, though, once. So that's kind of grunty. And also think to yourself, even if you think, hey, I can do integration by parts, this won't be hard. Think to yourself, gee, would this be a good idea to use all the time? Because what if alpha had been, like a 5 instead? Then I would actually end up looking at X to the 4th here. I would have to do integration by parts 4 times to get that integral. Grunt work. Is there a way to avoid grunt work? And yes, there is insight into the structure of the situation. So I'm going to define a little adjunct random variable, capital Y. That is the number of events in the time interval from 0 to 5 time units in a Poisson process where events come 4 time units apart on average, thus they come at a rate of a quarter of an event per unit time. Okay, so I've just set up a random variable associated with the Poisson process that you can associate with this gamma. And I would like to find the distribution of capital Y. Well, it's going to be Poisson because it's counting up number of events in a time interval, but that's not a unit time interval. So the lambda for this Poisson is going to be the width of that time interval 5 times the lambda for the Poisson process. And so x is distributed as Poisson where lambda is 5/4. And the thing is that the chance that you have to wait less than 5 time units to get your 2 successes, that's the gamma thing, is the same as the chance that the number of successes in those 5 time units is at least 2. And that would be 1 minus the chance that it's less than 2, 1 minus a very simple sum, just 2 terms in that sum for the Poisson PMF. So no integrating by parts, much easier. And you can simplify as much as you want. I decided to go this far. Okay, insight over, getting it done. Going to Wolfram Alpha to get the integral, total cop out, insight. Number 20 in section 3.2. So this is the one where you have a warranty. And there's like a formula for determining how much it's going to pay depending on when the device breaks down. And the time the device lasts is exponential with a mean of 5. So there's its PDF. And the formula for the value of the warranty as a function of capital T there is it's this if the thing lasts less than 3 time units, and you don't get paid anything if it's more than 3 time units. And we want to find what's the expected value of what you're paid. Like, what's the warranty really worth? And so I got to do integral from minus infinity to infinity, v of possible time times chance of getting that possible time. And the support of the exponential is only 0 to infinity, so I only have that range. And within that range, I've got that formula for f of t. And then I've got some thinking to do about v of t. Well, its support, as you can see from here, is only from 0 to 3. So I really only need to integrate from 0 to 3, and I got the formula for v of t now. Okay, so let me see. Look for ways to make this integral simpler. Don't go to Wolfram Alpha and just sort of ask for it. Ask yourself, is there a way that I can do this with some insight, into my calculus? One thing you can do is separate this into 2 pieces, like a tough piece and an easier piece. That way you can kind of focus in on the tough piece. So thinking about the tough piece for a minute, the tough piece, to get that tough piece, you are doing the 100, times the 2 cubed times 2 to the minus t times this 1/5 stuff. And 1/5 of 100 would be a 20. This 2 cubed is an 8. And so, 80 times 20 is a 160. That'll be like on the outside of this integral here. And in the other piece, it's much simpler. There's a 100 and the 1 and this 1/5 stuff. So there'll be a 100 on the outside of that integral. Okay, now focusing in like on this integral here. What's hard about it is there's 2 different bases. 2 to variable, e to variable. Why not have 1 base? So I am going to cleverly write 2 as e to the log of 2. And e to the log of 2 raised to the negative t is e to the log of 2 times negative t. So that is 2 properties of exponentials and logs stuck together to get this bit. And then I've got a product of e to different things, and so by another property of exponents, that's e to the sum of the powers. And within those, within that sum, I can just pull out a negative and pull out a t, and so I've got e to this stuff. Okay, and continuing along thinking about this guy, I've got e to a constant times t to find an antiderivative for. That's so easy. That's e to the constant over the constant. I'm going to evaluate between 0 and 3. And so I get to plug in my 0 and plug in my 3. All right. Next, let's think about this other integral here. And so this one is actually quite easy, because we know that the probability for an exponential to be bigger than a number is e to minus that number over the theta. That's something we've derived in class from integrating the PDF from the number onto infinity. So it's like in our head is a formula. Chance of being bigger than 3 would be e to the negative 3 over 5. We want the chance of being less, so that's 1 minus e to the negative 3 over 5. So you don't have to struggle with the integral if you remember some of those basic facts. It's not hard to struggle with this integral. I'm just pointing it out. And then you've got something that you'll have to like stick into a calculator, and or you can go to R, or even Wolfram Alpha, or even Google might even be able to get this for you somehow. But the point is to try to get down to where you've understood as much as possible what happens. Don't just like throw your hands up in the air when you see that integral. See if you can apply your calculus insights. Let me see, number 6 in section 3.3 on normal curves. So this one here was really easy for people, except I was a little puzzled sometimes. People didn't seem to want to use R. So like, you definitely understand that you're dealing with a normal random variable here with a mean of 166. And because the sigma squared over 2 part is 200, the variance is 400. But, so if you wanted to find this probability here, you could learn how to use the tables, but like that's this slow and antiquated way, and they just have it around in case people don't have computers. They're really assuming that people, like if the people like have a way to find on computers, then they'll go ahead and use computers because it's easier. So you could do P norm GC, concatenate the bounds 170 to 200, say region is between, mean is 166, standard deviation is square root of variance, and R will pop this out for you right away. Same for the other part. So like, I'm not taking points off if you learned how to use the tables, and transferred to a standard normal and went to the table for the standard normal in the back of the book. I mean, that's fine, but R is easier. Number 8, I graded this one kind of lightly because when I wrote down the density for the function, when I was giving you, when I wrote down the density for the normal random variable, when we were given the hint on the board about this problem, I left off the 2, okay? And so a couple of people started off wrong because of that. Well, anyway, once you get the right one, you take its derivative, and you're going to have to use the chain rule. It is a good idea to simplify what you've got as much as you can first before you take the second derivative, which will involve the use of the product rule and the chain rule within that. And you want to look ahead, okay? You want to look ahead. You're thinking, I'm ultimately going to be solving an equation. Second derivative of x equals 0. And so you're going to be thinking like, what kind of stuff is going to be stuff that's really not important in that problem? Stuff that like I could divide out in a 0 equals expression type of a problem. And so like this stuff here, that's not 0. I'll eventually be dividing by it. And e to this minus x minus mu squared over 2 sigma squared, that is not 0. And it's present in both of the terms here. See the plus there, there's 2 terms. Is present in the first term, is present in the second. That's going to get divided out. So I'm just going to like write it as, e to some variable. I'll call it e to the stuff, okay? And that makes what I've got simpler to look at. And with what's left, I can again think like, what's the easiest way to proceed? I would not multiply out x minus mu times x plus mu, giving myself 3 terms. Right now, I just keep it as x minus mu squared. Okay, here I am with my equation to solve, and I'm first dividing both sides by this stuff. And then I'm going to divide both sides by e to the stuff. And you can see the benefit of not having multiplied out the x minus mu squared. If you just keep that whole quantity squared, then you very quickly get down to this, which gives you this. Okay, and so then you just solve for the x. And you avoid all the hair. So avoid that by kind of like habit of like when you see a power foiling it out, think about like what's the most advantageous form to keep it in, considering the larger project that you're actually engaged in. That's insight, as opposed to just getting it done. Number 16, again, insight, and especially also avoiding internet. I'm sure there's somewhere on the internet somebody has suggested the quick solution for this. I'm much happier to see if you struggled and got something than if you found the quick solution. The quickest and most insightful solution here is to look at your three graphs and look at those three moment generating functions and think, you know what? I know something about moment generating functions. They can tell me the mean. The expected value of a random variable is the derivative of the moment generating function at 0. And when you're looking at a graph of a moment generating function, you can look at, in your mind, the tangent line to the graph at x equals 0, or at t equals 0. And so this might be kind of useful. So when you look at your random variables, the normal 0, 1 random variable has a mean of 0, okay? And so the slope of the moment generating function at 0 will be 0. And so you just look at those three graphs, and there's only one of them that has slope 0 at t equals 0. It's graph A. And the other random variable here, this normal random variable has a mean of -1, so you're going to look for a graph that has a slope of -1 at 0. So you pick out graph B because its slope at that point was negative. And whereas this one with the mean of 2 goes with the one that has positive slope, graph C. It's the only choice left. So that's the most insightful solution. And it's great if you found that on your own. If you didn't really struggle with it and went to the internet, I can't tell, but don't do that. Really try to struggle. And if you can't find the insight, ask. Make a little note in the homework, and we'll definitely talk about it. Okay, that's all I've got for this homework go over. See you later.